Okay, dear colleagues, good afternoon. So let me open the last, I would say, mini course of this summer school and introduce our speaker. So it's my pleasure to introduce Stefano, who is an IEEE fellow, vice president of EU robotics and professor and head of the Robotics and Mechatronics Department at University of Twente, and also the head of the Biomechatronics and Energy Efficient International Research Lab here at ITMO University, and also a great guitar player, by the way. So his lecture is on energy-aware robotics, and in many cases it will be continuation from what we had in the morning from Arjen, and probably with more applied examples from robotics. So let's give a floor to our speaker and let's give an applause.
Thank you. Well, thanks a lot for the introduction, for the invitation, and thanks for being here with this heat. If I fall asleep, wake me up while I'm talking. It's really unbelievably hot now. Okay, so indeed I will continue on what Arjen has been built upon, because all the things I'm doing in robotics has basically built on this paradigm that Arjen has introduced, and I will stress a few things, and namely I will apply it for interaction, for robotics interaction, which is very different than the paradigm that usually it is used in robotics. So here are some of the paper and references that you may look at. This will be uploaded then after to the site, so you can read it. And namely, I think the first and this one, energy in robotics, that will be the two things, the two documents that you will be able to find most of the things. Before starting, I want to give an introduction about the context. You know, everybody's talking about AI. It's like, you know, there's no word for anything else than AI nowadays. To be perfectly clear is that people do not know what they are talking about most of the time, because if you think about this man, if you scale your brain, the part of your brain, you scale it, you look at the cortex of your brain, and you scale the part of the body volumetrically in relation how much part of your brain is used to steer them. You get this thing. It's called the critical homunculus. And what you see, it has huge hands. So a lot of part of the cortex is used for steering hands. And that's why, by the way, humans are the top animals in our kingdom of animals, because you learn a lot. And it has to do with interaction. For the men that have a lot of egocentric things, you see the penis is very small with respect to the hands, okay? So really the all sensitivity of the hands and the motoric of the hands is fundamental for that. So in robotics at least, it looks like everything can be done with the algorithms that basically can make calculations and everything can be learned. Well, of course everything can be learned, but people very badly underestimate the complexity of the hands and the interaction. And the real sweet spot in robotics, which is we are far from having really decoded how to do things, is the intersection, and why you learn and what you learn about interaction, so which is the physical interaction. To give you an idea of what I'm talking about, just want to show you some videos. I mean, look at these guys. That's certainly not me, but I mean, you will not be able to build a machine that does this kind of things unless you are able to really control the interaction, which is not a signal, which is not a force, which is not a position. So forget about regulation in this kind of things. If you go building machines that can do like that, forget about this a paradigm which tries to control the force. No way. And in physics, if you think about how engineers went far, if you look at these examples of planes, these are, as long as I know, unless there are some more secret one in Russia that I don't know, I can know. The Blackbird is the fastest plane which is at least publicly known, which is 32, it can fly 32 body lengths per second. Okay, its length per second. And it is nothing compared to a Swift. A Swift, you know, a small bird, it can go 140 body lengths per second. And if you look at a Douglas A4 Skyhawk, it has a roll rate, it can rotate up to 720 degrees per second, but a little bird can do about 5,000 degrees per second. So, you know, and that is the top of the line. So we are far from being able to repeat this. And why I use the example of birds, you'll see it at the end. Some people know why, but we'll see it at the end. So what I think it's very important is that when you talk about interaction, forget about the standard paradigms in control. That is not what you're going to need if you want to be able to do this kind of things, okay? So what I will do is I will concentrate in using a physical structure that Arjan introduced, because as long as I'm concerned for the things I'm working on, it's the only way to do it, okay? And I want to try to control the behavior. And I will explain, actually I can do it briefly now. So what you do normally if you have a robot, okay, and usually if you have a robot, people say, if you suppose this, I have a robot here, okay, and what people often say is, okay, this is my environment, okay, and people say, I want to control, for example, the force. Here is where they interact. Suppose I'm touching this table, okay? And in robotic control, people say, okay, I want to control the force I apply to this table, or I want to control the velocity or the position of my hands, okay? Well, too bad that if you, this is not well-defined problems if you're talking about interaction. And the reason is very simple. I just want to give you an example to let you understand what I'm talking about. Suppose I have a mass on a plane, no friction. Let's call it a robot. The simplest you cannot think about it, okay? This is a mass. Okay, and you suppose that you can apply control to this mass, and the control you can apply is basically a force that you can apply to this mass, and you can measure something from this mass. Okay, and you want to interact with something, so here's the hand, the guy with the finger, this is a very ugly hand, and it touches this mass. Now the question is, if you want to control the position of the force here, where it touches, it will not only depend on yourself, it will depend on the environment. So that is not a well-posed problem. Let me be more precise. Suppose I want to control the force applied to this table. I apply a certain force, but the table is moving, and then it falls out, and I want to apply a force. I cannot apply a force, okay? So the same situation, if I want to control the position of my robot, and this is full concrete, okay, and I want to apply a position is 2 centimeters in the table. There is no way I can do it, okay? So what I'm trying to say is, you have 2 dynamical systems. This dynamical system called the robot, for which I can shape the control, right? And you have a dynamical system which is the environment. The function of time of position, force, velocities will be dependent on both. So you cannot, it's not well-posed problem to say I want to serve a certain value here. What you can do is that I want to control a certain behavior. Let me give you an example. You can think about saying, okay, I want that my robot behaves, for example, like something like this. Okay? Now, and this would be control, right? By control, we behave something like that. Now, this is, for example, a certain damping, and this would be a certain stiffness, and this is a virtual position. Now, you see that now, whatever I do, if I can have this behavior, the position and velocity at the end effector will change. But these parameters which I control, like the mass, the B, and the K, those are structural parameters which I can really control. That's the behavior that I want to enforce. Is that clear? Yeah? Okay, so furthermore, what is also very important in this context, Arjan gave a fantastic introduction. Energy is the basis of physics. I am personally not interested in something which is not physical. Okay, so because robots are physical systems. So if you try to do things on a physical system, but you do not look at the energy and how that the controller interacts with energetically with the system, there is no way to have situations of passivity in all situations. I'll give you examples on later. Robustness is a big problem. The environment cannot be properly modeled. Suppose you want to do a robot that shakes hand to a human. I was telling that at lunch. If you want to talk about stability, and you have two dynamical systems, of which one is the control robot, you know pretty much a lot about it, and one is the human, because that's the dynamical system, how the hell are you going to prove stability about it? You tell me that you have a good model of a human? Bullshit. Okay, there's no way. And you can have unexpected behaviors. Instead, if you use energy or better energy awareness, so you do everything by not forgetting that what you are doing is controlling a physical system, you need to track and control. You can track and control the energy flows. That is something that Arjan mentioned it. I will go further in that. You have never problem with stability. I will show you how. It's a theorem that I can show you later. You are intrinsically robust. If you have, suppose that this is your robot, and this is your controller. Arjan was mentioning this. This is your controller. Suppose that I can, and I'll show you how. This is in discrete time, because you will have sampling and stuff. But suppose you can actually build something like this. Suppose you could physically build this thing. This cannot get unstable. This is intrinsically passive, right? So you have intrinsic, and even if I would have this damper and this spring, and I built my dynamics based on this mass, but this mass, instead of being 1 kilo, is 100 kilo or a milligram, still it is still passive. You know, it will behave differently, but for safety and passivity, that will be fine. And what you will see is that you can easily couple the discrete time and a continuous time in a very simple way, which will ensure that you always behave properly. Another issue, time delays. How much work is it in time delays? If you look at these things, that, as long as I'm concerned, is a completely solved problem. There will have no problem with time delays in computation or in transmissions. I will briefly talk about it. Another thing is geometry. Geometry is, in my opinion, far too often underestimated in education and in research. Okay, so very often you have a lot of complicated equations. You don't see the structure. How can you reason about equation if you don't see the structure? Okay, it doesn't give you insight, as long as I'm concerned. That's at least how my brain works. Solutions are always very often dependent on coordinates. If you do not do things coordinate-free, what doesn't make sense if somebody uses other coordinates, gets a different solution? You're talking about physical system. It's not that the physical system should behave differently if you use different coordinates. Or the law of physics are invariant, okay? There are some things, for example, in robotics, I could mention many papers about it, that in this respect, people, for example, base an whole algorithm by taking the eigenvalues of a matrix, which is the inertia matrix. Okay? This makes no sense whatsoever. If you give me any inertia matrix, and you give me a set of eigenvalues that you want that inertia matrix to have, I will find you coordinates changes that will give you exactly this eigenvalue. So what makes the sense of calculating eigenvalues? It's not invariant, okay? And there is a lot of things, and this has to do with geometry. So everything you do, there is one suggestion to give, is look at this stuff in general when you work. Because if you look at geometry, you have very simple descriptions of what you want to do, certainly physics. You are coordinate invariant, the physics is respected, you have no coordinate in singularity which are dependent on coordinates. A typical example, if anybody of you working in robotics, is the rotations. Okay, you know that rotation has a very strange topology. It would be nice to talk about rotation the whole 3 hours, but what is known in the topology of rotation is pretty nasty. Okay, and people use very often in robotics, for example, what are called chart in differential geometry, use Euler angles to describe rotation. It is well known that, of course, you cannot cover with Euler angles the whole rotation group. Okay? And then you get singularity if you are not careful about it. Instead, there are methods to do it properly and without any singularity. And again, projections. That's another thing that you see it again and again. If you talk about projections, and also Monday there was something about projection, it can be made invariant properly, but you cannot define if you take a projection on a subspace, you have to be careful because orthogonality, as if you are in Euclidean space, you know that you can define orthogonality. Well, if you have orthogonality, if you have an inner product, okay, that's fine. You can always define orthogonal complements and stuff. But if you are, and certainly that's the case in multi-body dynamics, you are a 6-dimensional space, and I'll say a few things about it, but you don't have an inner product. There is no invariant inner product in a space of motion of rigid bodies, okay? So you cannot take orthogonal projection. Makes no sense. The only thing you can do is to define just something I hammer all the time when I discuss, because I think it's, certainly students have a lot of misformed brains by bad education about it. So if you have a subspace like this and you have a vector, and you say, I want to project this vector here, everybody would do like this, right? That makes no sense. This implies that you have defined a complementary subspace, which is this, okay? But in general, if you don't have an inner product, it depends on what subspace you define. Suppose I define this subspace, the projection of that vector on this, along this subspace, would be 0. Okay, so it really depends. Be careful about geometry and the choice that you make. And this is the point I want to talk about. Because in the case of multi-body motion on kinematic pairs, I will not have I will not talk much about it. But this space will be something which is called SE3, which is a 6-dimensional space, and it has no inner product. So when you want to talk about the composition of motions, you have to be precise. Otherwise, you make assumptions which are nonsense, okay? So geometry is very important. Furthermore, this is actually would have been something nice to do to show you before Arjan's talk. Because this is something I show all the time. Some of you have seen this before, but I love this thing. Because to make a point, I will make it now. So, do you know what this is? Yeah, so some of you have seen it before. If you haven't, so the one who has seen it before, don't talk about it. So this is called the dovetail, okay? So you basically have, it's something you find everywhere. It's basically to constrain 5 of the 6 degrees of freedom that you have between 2 rigid bodies. And one of them, it's free. And then you basically assemble, you put a screw, and then it's fixed. You find it in kitchens, wherever. Okay. Now, for those of you who haven't seen it before, do you think that these two things can move? The red and the gray. Right? Who thinks that can move? Who thinks it can't move? Well, that's exactly the point I wanted to make. Well, it can move. Okay? And, okay, now you see, okay, well, you tricked me. Are there other solutions? There is clearly a symmetric solution, 90 degrees. Okay? Are there more? Now you start thinking. Okay? To be a bit explicit, you fuck me once, you will not fuck me twice. Okay? Well, it turns out that you have an infinite number of solutions, which are all solutions which are basically hidden. This is another one. Okay? There is another one, I think I have 3, 4. But I mean, why do I show you this? I think this is a typical situation in which if you have been used to see things always the same way, you don't see what is behind. Okay, so if in control, and certainly if you're doing control in robotics, you've always been looked at regulation problems, control of position, of forces. That's the way you think. You don't think differently. And instead, the paradigm that, of today that Arjan started to introduce, it's different. You look at the way, you know, it's not just about signals. Physics is not about signals. Physics is about physical interaction via energy. And the structure you need is the structure of power ports that Arjan introduced this morning. Okay, so what I will talk about is these 2 hours are 2 things. The first one is energy-aware robotics. And the energy-aware robotics will be basically how can you handle robotics and some tricks that Arjan already anticipated. And then I will talk about something a bit more advanced, but very, very, very basic. So I want to give you, to show you that if you want to interconnect parts which are very complicated, if you want, for example, a network of resistors and inductors, there is not much geometry there. But if you want to talk about multi-body dynamics, that's a different ballgame. If you want to model a human being with all degrees of freedom, that's a different ballgame. Okay? And you'll need certain other structures, which I will not, I will tell you why you need that other structure. and how to do it, okay? In principle, in intuitive terms. I will try to will be different than the lectures before. I will try to minimize the math, but give you more the intuitions, okay? I can give you a lot of math if you want, that's not a problem. And if you have questions, I have the boards, that's not a problem at all. But I try to minimize and really stay more on the level of concept. Okay, energy-aware robotics. So first I give always this example, which is actually, once again, it's clear from what Arjen showed, but to show that about signals and ports, what's the difference? Look at this. What is this voltage divider, right? So you have here a voltage divider with two impedance, let's say two resistance, whatever. And under hypothesis, you have an infinite impedance here, so then you can write a transfer function, right? The transfer function tells you, okay, if you have a certain voltage here at the input, that's the voltage at the output, okay? Fine, everybody has seen this once before, okay? Now the question is, if I give you this network now, you would be tempted, and now you know I made the mistake, I tricked you before, so you will not be tricked once again, likely, but I'm pretty sure that if you ask this to a number of students, they will tell you that this is the solution. Just take the cascaded of the two transfer function. This is of course not the case, okay? This is not true, because in the previous, when I calculated the transfer function, I made an hypothesis. And my hypothesis was that impedance load was infinity, which is not the case now because I have another voltage divider, it's not infinity load. Okay? This would work if I would put here an op-amp, an operational amplifier, which completely isolates the physical system from each other. Then would it be okay? But if you do this, this is wrong. Why? Because physics is bidirectional. You cannot just talk about a velocity goes in one direction because the current goes back, okay? And these things of velocity and current, forces and velocity, current and voltages, velocity and forces, these duality issues of efforts and flows that Arjen showed, that's physics. So you cannot do anything about it, then use this method and always consider them together if you want to talk about physical systems. That's it. Okay? If you don't do it, you're prone to error in the physical world. Okay? Good. So, also the issue of robustness was mentioned a couple of times, and this is an example I was doing for the table. So what is interaction is nothing else than this, right? So you have basically a robot that you control, whatever it is, and you have here your environment, the hand, the wall, whatever. Interaction of the robot and the environment will be bidirectionals, okay? And this is the issue I was mentioning before on the behavior. You know, you can control how my system will behave if, with the environment, I cannot control only this variable, because this variable will depend on the other one. Okay, it's bidirectional. So, as introduced this morning, this is actually the paradigm that you need. You have a control robot, and then you have the environment, and you have these bidirectional signals. And this is causal. Now, it was not presented as causal. In principle, physics is you can describe everything acausally. And I will show you, I mean, this representation that Arjen has shown, it's completely acausal. And there's a lot of advantage. So actually he presented two situations. So you basically had the situation in which, suppose that I want to describe the behavior of my controlled robot, okay? Then you will have, and you have something like this, effort plus F flow equal to 0, where these efforts and this flow will be the two variables which are there, okay? Now this is acausal. I don't tell you I just say there is a relation between efforts and flows, right? And the environment will be something similar. So this is, let's say, the robot, and the environment would be something like that as well. Environment F, okay? And once you have these two things together, then you can solve these things and you will have the effort and flow as a function of time. That's the idea. Now, if you have a causal relation, basically you can, and this is what Arjen also showed in the other things, suppose that, for example, this is invertible, okay? You can write this same formations as effort is equal to minus E inverse F. This R, right? Now you have expressed the causality. You say that basically my robot gets a flow and generates an effort, or the other way around. Okay, but in principle, it's completely acausal. Good. Now the structure, Arjan didn't go in the geometry, but in mechanics, the structure is very important. The geometry is very important. So, electrical mechanical domain, you have basically, if you are in scalar situation, you have currents and flows are real numbers. No geometry there, it's a scalar. Okay, but when you start talking to mechanics, and you get to rotational mechanics or rigid body mechanics, then geometry plays a role. And then these efforts and flows are not just a bunch of real numbers, are geometric entities. You know what a covector is, duality? So you know that what a vector is, you learned to talk about vectors. A covector is a different thing. A covector is a linear operator from the space of vector to real numbers, okay? And if you talk about mechanics, velocities are vectors, forces are not vectors, okay? Forces are covectors, okay? They transform differently. And if everything is orthogonal and stuff, you don't need to bother about it. But if you talk about multi-body dynamics, nothing is orthogonal. So you have to bother about it, okay? And the geometry will therefore be given here, and I will tell you this is actually our Lie algebra of a Lie group, and I will tell you why you need to talk about Lie group at any case. That's the second part of the lecture. And you can go to continuous mechanics. I'm going to show you something about it, and the geometry that you need there is even a bit more complicated. And it talks what actually are differential form, Grassmannian algebras, in which you have to introduce new concepts, this duality, and how do you define the Dirac structure, and things that Arjan mentioned before. So it is important to realize that in this business, you need something like Lie groups, and this will be the second part of my talk. So this is the general structure system. If you want to model any physical system, will look something like that, in which you have. This is the Dirac structure. Just think, I always use if people are, just think about these yellow things as pipes. And you have water. The water flowing through this pipe is energy, and is uncompressible. Okay, so if you pump water here, the water will come out somewhere else. And if you pump water here and pump water here, it will have to go there. If you pump water here, here, and here, and here, it will have to get out from that. There is no other option. Okay, so the total amount of water going in is zero. That's the fact that what Arjan showed, that is power continuity, okay? Then you have elements like this. This is like the C element is like a balloon. It's a plastic balloon. If you pump water, it gets the water, it's a storage, it's a tank of energy, right? And the energy, if it goes down, it can go back to the system. And then this is a very nasty guy, which is what is called, here is the RS, is a damper, is the energy reversible transformation of energy, which basically goes, normally speaking, to a domain which you can't avoid. That's what you normally do in engineering. If you do not look at the thermal domain, you use what are called free energy, what is actually called free energy. Basically, you say, okay, energy is dissipated, but of course energy is not dissipated. Energy in the universe is constant, okay? And the energy is basically irreversibly transformed to heat, and then you can gain it back, but then you lose some stuff, the entropy increases, blah, 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 okay? So, but this is basically what you talk about the resistance. In physics, if you want to talk about electrical networks, very often you say, okay, I have an electromagnet, I have a resistor, okay, and then you forget about the heat. But of course, what the resistor does, it generates heat. So you can model a resistor as something which is basically, and this is a bond graph notation, which the sign has a very specific way of working. And you model it like this, where this would be the voltage and the currents that you would have see here. This is the voltage and this would be the current, for example. And then you say, okay, this is power that just goes away. But if you want to consider the heating, so the thermal domain, this is actually indicated as RS. And you continue. And this is the thermal domain, where you have here temperature and entropy flow, which is the product is, again, power. And the power here is the same as the power there. But that is irreversible, okay? And this is, you can model everything this way. And this book is a book where you basically find all the things that also Arjan described as a kind of a major reference. But what I'm doing is multi-body dynamics. And if you want to model a robot then, in this way, you can use a Lego. I mean, the cool thing about this interconnection is you really have a very open way of doing things, like a Lego. You have blocks that describe things, and you don't need to know anything about the rest when you want to use this block to interconnect it to anything else. You cannot do it with different things. I show you these voltage dividers that you can't. Okay, but if you do it with this Dira structure framework, you can. And then you can do it for multi-body, because in multi-body, you can describe, for example, a set of rigid bodies, a set of springs, a set of dampers, of dissipations, and the motors, and then you have the network connection. These are the Dira structures, and you can build the whole system. What is important is the topology of this network is not, in general, the physical topology, it's the energy topology. This is a mistake that also sometimes in discussion, some question. If I tell you, if I give you these things, okay, and I tell you this is a resistor, okay? Suppose I have a resistor in my hand, there are 2 wires, okay? What are the physical laws that describe this? Easy. Physical law. Eh? If I throw it to you, do you feel Ohm's law or something else? Eh? Well, it's a resistor, has weight, doesn't it? So what I'm trying to say is it depends what you model of something, right? So that's the issue. And usually, I didn't throw it to you, but usually I go to the student and I let it fall on his head. Did you feel a resistor? Okay? But what I'm trying to say is, what do you want to model? Model is just a way to describe a physical thing. So the resistor itself, it's not Ohm's law. If a resistance goes in a car, it's weight. If you throw it to somebody, it's weight, okay? But also purely in electrical domain, a resistor can be a pure resistive feature. I could have capacitance and inductance. Those are the effects I use, because those are the effects that shape the dynamics and the energy flows. So please make a distinction between the resistor and the description within the resistor. What you do with this stuff that Arjen described and I'm doing, you talk about the physics of energy flows within it. So if I draw an R there, it's not the physical resistor, it's the resistive effect in maybe a resistor, okay? All right. And then you can model all these things, and in fact, you will have this situation which you have here a control port, and you have an interaction port, which is what I started off with. This is where you interact with the hand, for example, okay? And this is model, which is completely, you can describe it completely independent of what you control you use and what environment you touch. It's completely open. And it has, again, this structure in which basically this R here will be all the damping, and this C here will be the storage of energy, kinetic, potential energy, and all these kind of things. Okay. So the conjecture, which actually can be proven formally, is this: that to ensure stability during any robotic interaction, control needs to be implemented by interconnection. And I will go more, Arjen already introduced it, but I will go more in this. Either physically or by control. What do I mean with that? First of all, what is control? Okay, when you think about control, you think, okay, you measure something, you use your computer or whatever nowadays, you do calculation, you steer something. That's control. But control is also building a machine in which you take a spring and you place the spring in the right place. Control is changing the dynamics of a system you're given, okay? So that's also control. So you can do it by like that. So suppose that now, and you know that with what you've seen this morning, you can model everything with this framework. So what you could do is to say, okay, I model my mechanisms, and then for control I could say, you know, I have a spring which I can model in the same way. And Arjen showed you that you can, it's basically an algebra. You have Dira structure, you have a Dira structure, you can formally prove that you can assemble, you have a new Dira structure, and you sum the energy, okay? It's like an algebra, which stay in the algebra. So you basically, what you do something like this, you get a new system, in which you interconnect the spring to the mechanism. And this is your control system, which now has a new port, if it has before, depending on how you build it. And this is one way of doing control by interconnection. This is physical interconnection. You basically take the spring, you solder it on the machine, okay? And this is very useful. What you can do, actually, what we did, for example, I will come to that later. We are doing here at ITMO, we're building a cheetah. But this is something I did in the past with somebody from MIT, the MIT cheetah. And one thing was, for example, you have a back and the front of the cheetah. And a lot of cyclic energy, you want to, why is a cheetah going so fast and it's so amazing? Because it's not doing control by signals, but it understands the physics, okay? So but basically, there's the muscle structure and the springs and the tendons in the spine are such that it can use the energy very efficiently. So basically what we did, if you want these things to locomote, all the force that you would actually inject and damp by normal control, you can do it by placing a spring in the right place, okay? And this is actually what we did in this work. I will talk about this more specifically later. So this is physically, we put a spring in the thing, and we're actually doing something similar here. Okay, what we also can do is, for example, to say, by control still physically, what you can say is, very often when you have something that oscillates, mechanical system, what do? You inject damping, yeah? And inject could be by control or could be by putting material. You know, if you have for example, I play drum and also, so if you have something that vibrates, what do? You put something damping, some mass, and you try to damp it like that, right? So if you have a machine that you want to stabilize, damping may be a solution. But damping has disadvantages because it solves your problem, but it costs you energy. And if you have a mobile device, that's not what you want to do. So you can achieve the same, but you can store this energy somewhere. You can be much smarter than that. And you can do this in this way. So what you can do, you see these RS I talked about before, you can do something that if you look at it from this side, it feels like a damper. It definitely feels like a damper. But then what you can do is basically, instead of building it like a damper that physical heat is generated and throw away in the air and then change the climate, you can basically make something that feels like a damper, but actually that energy is not thrown away, it's stored, and whenever you need it, you use it again, okay? And this is actually something which works very well. This is a patented device that we built. This is a prosthetic device, which is basically what it does. You see this line here that connects the upper femoris to the angle down there. And what it does, basically this extension is basically a spring, okay? And when you move the leg, you have kinetic energy in the lower leg. When it's straightened up, that kinetic energy is basically stopped with this spring. And it's done in such a way that when the leg is straight, that energy is completely in this spring, but then it's blocked. It doesn't come out anymore. Okay, it's like a damper from the side of the motion. What Okoboch and Osur, which are the leader in the world on this, are two enterprises that send a lot of prostheses. They have a rheologic knee. They have a knee that basically, with the fluid, the brake energy is gone. With these things, what we do then, this energy, you see this switching here. In the next step, that energy is used for the energy of the gastroscema, which is this muscle, because walking is nothing else than falling all the time. So what you do is, you higher the potential energy, you fall. Okay, next step, you higher, you fall. You higher, you fall. Okay, and then energy is regained. In this way, we regain 80% of the metabolic energy that would be just thrown away. Okay, so this is a much better device. So this is this idea of basically using the energy but of course you can do control, and I'm going to say the most standard way of doing control, but then without losing these features, okay? So this is one way of doing control, but how can you do it properly? And this is these things I mentioned before, which is about the a theorem that I proven formally, which basically tells you this. Suppose that this is my control robot. This is the port, which is the port I interaction with the environment. So this is the interaction port. Well, I prove it formally, and the proof is amazingly simple, but it had none before, is that if you give me, if the system, now I'm looking at the system from here, okay? If the system is not passive, or let's say the energy which I can extract from this port is not lower bounded, so the system controlled system with the control and everything, I can extract energy, okay? I can prove that I can find constructively an environment which is passive, which is lower bounded, but such that if they touch each other, the system becomes unstable, okay? And this is pretty interesting because I'm saying basically that if you want to have stability in interaction, at least for a passive environment, whatever structure it has, is a table, is a floor, is a human being which is passive in principle, the only thing I can do which I have no structure information is to make this system with the lower bounded energy, okay? So it is really a necessary condition for stability that you have, that the control system is passive, that you cannot extract energy out. Okay, so what does that mean? Well, it means that immediately I can exclude state feedback in the standard way of the world. Because if you do state feedback, you lose what is known as collocation. So if you measure something and you actuate something else, okay, you lose track of energy flows immediately. Because you know what collocation means? If you have collocation, it means that if you have a motor, with the motor you apply a certain force, that you can measure the corresponding dual variable in that spot. That's collocation. You know that if you have, for example, a motor here, and you have an elastic torsion free, and you measure the position here, you know that you can have vibration. Stability becomes an issue because you have no collocation. But you know that if you measure here, then it's not a problem because you can always monitor the energy basically that you inject in your system, okay? And basically the idea is that if you do state feedback, you measure here and you actuate here, okay? So you can always find situations, for example, if you do your state feedback based on model base, you have a certain model of your plant, and the plant is not, I mean, you have a wrong model, and the model by definition is wrong because when you touch the environment, you don't know what you touch. Okay, so the kind of disturbance is not the disturbance, the whole purpose of your thing. You want to touch things that you don't know. That's not disturbance, it's what you want to do. Okay, you see my problem, so you really have to think differently. Because the only way to do things right is to do control by interconnection, okay? Why? Because if you do that, you can solve the problem. So how does that work? So this is the system, okay? And so suppose that this is your robot. The first step you can do is to say, okay, I put actuators. Actuators are a physical device, which are passive. An actuator has a mechanical part and has an electrical part. So far, so good. It's still passive, okay? So what you do then after the actuators, you put amplifier, right? You put a power amplifier to drive your motors. And there is where it starts getting nasty. Because what do? What you do, you connect this to a power supply. Okay, so what you actually do is that now you have either a battery of a power plant behind, and you can have an energy flow to your system, which is unbounded. Okay, so that's something that you don't want, because I show you that if you do something like this without think about it, what happens when you are here, you can extract that energy in a way or another, okay? And basically you can get all the energy from the power plant close by, and the system can get unstable if it touches an environment which is even passive, I showed you, okay? All right, now, what can you do about it? Well, you can do something. This is the continuous time, we are in continuous time, now the physical devices. Now, so if you do control like this, and what I mean with this is you just measure something, the actuate, this is prone to error. Because as I told you, it will not satisfy in general the fact that you can extract unlimited energy from the environment. So you have to do it differently. And the first thing you need to do is to virtualize the energy flow. So what you want is that your power amplifier have, of course, they are attached to the power supply on one side, and on the other side, if they are a transistor bridge, H bridge, I don't know if you are electric engineer, whatever, you have the signals that you control your power amplifier with, okay? That's the value that determines And from there, you determine how much power, physical power, you inject. Okay? At the basis of your transistor, of your MOSFET, whatever. So you want to do something like this. Okay? And then what you do, then you are in the discrete time. You see, I changed the color. Now everything which is now in orange are like, I want this to behave like power bonds, but now it's virtual. Here's physical energy. It's the real stuff. You know, the energy that in Joule, that if it falls on your head, you feel it. Okay? This is the virtual one. But I want to do things in such a way that whatever comes here is the same than here. Not, so basically, this physical energy comes from here, clearly. But I want to do it in such a way that whatever goes here is the same as here. Because then I can build a controller which knows what's happening physically. And that's the idea. Okay. So that's the real virtual energy flow. So, and can you build this coupling? So this is this issue here, because, you know, very often when you do control standard speaking, you say, okay, I have to develop control a physical system. How do you develop your control for discrete time? And you say, okay, if I have a high enough frequency sampling time, then you can do the control design in continuous time, and it's okay. Or you do complete discrete design. That's another option. But here's different, because it's not just about the signals. You want an energy consistency. So what you can do is actually very simple, and is indicated here. Suppose that now you have a robot, and you have your controller. And what I see a lot of reflections. So you have here in the middle, you have a zero holder hold. And suppose that your controller sets a certain force, current. Usually a current amplifier, the level of amplifier, then you have a voltage loop. Suppose you have a current amplifier. So basically you can set a current that you want to have on the armature of your motor, which will result in a force, right? And this is furthermore a zero holder hold. So it means that it keeps that force constant for sampling. Okay? So look at this. What I'm doing is the following. Suppose that the time for you guys goes in this direction. So if here's K, this is K, and this is K plus 1, sampling speaking, okay? So what I'm doing here, I'm saying, okay, I measure the position here. I'm talking about one direction, one motor for the time being. I measure the position, and I set the force, okay? And then things move. The force is constant because the zero holder hold will keep that force, independent of what the thing does. Okay? So the force is constant, and now I'm at K plus 1. What I do, I measure the position again, and I set the new force. Okay? What can I say of what happened? Well, the force I know because I set it before, so I know that force. And I know the position when I started to set that force and the position now. Well, it turns out, which is pretty trivial, that if you want to calculate, and now I'm not approximating, the physical energy quanta that was exchanged from here to here, this is not an approximation, this is physical energy. What is the physical energy? It's the integral of the product of the force and the velocity, the physical ones, not the physical one. The force I know because I set it and it was constant. But that is constant, you can get it out of the integral. Okay? So you are left with the integral of a velocity. What is the integral of a velocity? A position. That's not an approximation, that's physics. That's what it says. If you have a velocity integrate, you get a position. So what you see here, you see something that looks like Euler integration, but it's not. Because what I'm doing, I'm saying it a posteriori. I'm saying, if I was here and I'm here now, I know 100% sure that the energies that I exchanged from there to here is exactly this. If this was a millisecond or was 300 years, that's right. Okay, it says, wait a minute, for 300 years, what's happening? Well, of course, what can happen, if the dynamics of the system is big enough, could happen that, for example, I measure zero energy exchange from here to here, but what could happen is that, for example, a lot of energies went out, and then a lot of energy came back, and then I measure nothing. But what you can have, if the sample time is not 300 years, but is decent, okay, that at least you know that you are not making bullshit at the end, that you can exactly know how much physical energy has been exchanged with the physical system. Okay, but that's exactly what we needed, what we wanted to do. Because then I know how much energy went from my amplifier to the plant. So if I have a variable in my discrete controller that you say, okay, this is the energy that I want you to use, and it was 100 value of that variable, and I measure that I gave 1 joule, 100 joule, I just change the value of that variable to 99, and everything is perfect. You see? Well, does that work? Well, it works pretty well, actually. So if you have this, and you do the sample, oh, wait a second. Should be a video to show you that it works. Wait a second now, because I want to show you this. Strange. Oh, it comes back later, okay. Yeah, no, okay, it's later. And then once you have done that, you took care about this balance, the energy balance, okay? So now we solve the problem of interconnection between the continuous time and discrete time. And then you have, this is actually what I showed you before, and then you have the fact that you want to do your control design, okay? And what you want is to make a control design which is physical. Because if you have a physical equivalent kind of controller, with physical elements like springs and dampers and whatever things that are passive, then you know that now, from here, whatever I do, I can never extract more than the energy that I have at my disposal. Everything is done on the basis of energy balance, you see? Okay? But of course, to do work, you need energy. Okay? If you ask a robot to, bring me these bottles, bring it upstairs. You need energy, of course, okay? So how do you do? Well, it's clear that you will have a supervisor, have a lower frequency rate, which will basically say, okay, you need to do that, that's a budget I give you. You're too young to have kids probably, but when you have a kid which doesn't know about money, you do not say, you don't give a credit card. Okay, you'd say, okay, you have here $10, buy this. Okay, and that's what you do, and if it comes back, it was more expensive, okay, I give you more. Okay, you see, but in that way you're sure that your bank account isn't going to hell. The same story here. And this is exactly what humans do all the time. If I give you this bottle, and I place this bottle here and I glue it on the table, and I'm sitting here and ask, could you bring me this bottle? What you do, you go there and you do like this. And then you say, what's going on here? You replan. Okay, and that's why humans are so stable in every kind of interaction, because everything is feed forward, basically. You plan the energy, you plan the planning, the path planning, and you actuate. And if something goes wrong, you replan. Okay? All right. So let me give you an example. This was actually something that Arjan already showed, but he didn't show you the nuances of this, which is something that I did many, many years ago. Suppose that what you want to control is this robot, this mass, okay? And I want this behavior. So I want that, what I told you, I don't want to control force and position. I want to feel certain things, a certain stiffness. I want to feel that stiffness, and I want to have that damping. So if I basically put this and I kick it, that's a certain behavior. Because if I want to pick, for example, pick up an egg, and I don't know very much because I don't have my glasses, okay, you will not pick it up very precisely. If you see exactly what to do, you can go very precisely. But if you have very stiff hands, a very small error in position will give you a very high force, and you break the egg, okay? But if you have something which uncertainty plays a role in your interaction, you want to be compliant, okay? So this is what you want to do, but there are these two conditions which are true all the time. Okay, one condition is that position measurement is available. You don't have velocity measurement, and you have saturation of a force. So the force that you can apply with the motor is bounded from up and down. Every motor, you cannot buy a motor. I mean, you can, if I give you a 500, I cannot ask you to control it to go as a Ferrari. Okay, the motor is there, it will be limited. Okay? So, and I'm going to show you, you can build something like this, but I didn't tell you what the advantage of this is. So this is clearly, this will be my controller, Okay? And now I tell you, and actually there is something, an idea I have about system reduction, which is pretty cool, I think, but I will not talk about that. So what you have is this controller, and suppose now that this stiffness is much higher than this stiffness. Okay, this is a spring which is much stiffer than this spring. And this mass is much smaller than this. Now, if I touch that mass, what do you feel as stiffness? If this is much stiffer than this, you feel this spring, right? It's a series of two springs, so you feel the one which is more compliant, okay? Less stiff. Okay, fine. Second thing, why do I do this in the first place? Well, you know, I need to put a damper, because if I don't put a damper, these things will keep on oscillating. But if I put a damper here, what do I need to implement that controller? I need to measure, to have a velocity, right? So how can you do if I only have position measurement? I say, okay, well, you take the measurements, I take the time derivative. Is that a good thing to do? Of course not. Certainly if you have a tag or noisy measurement, that amplifies the noise. You don't want that, right? Okay, that's good, okay. You could do something model-based, maybe, an observer or something. Okay, that's an option, but you need to know the model. If the model is wrong, that you can have some problems. You can do state variable filters. We were talking about, you know what a state variable filter is? You know what state variable filter is? It's a trick. Let me redraw what we just were discussing. But it's something which is a very nice trick. You don't want to differentiate, right? Because that's bad for noise. But what you can do is integrating. That's not a problem. So what you could do is something like this. Okay. So suppose that I make, this is a second order linear filter. Simpler, you cannot think about it, okay? And now suppose that you choose this gain such that the body plot would be 0 dB for a while, and then it goes down. What is the roll-off? It's 2 second orders, 40 dB per decade, okay? Fine, so if you have here a signal, which is in this bandwidth, what do you see here? Same signal, fine. And what do you see if you peel it out? This, oh, sorry, not this one, but this one. Not from here, but here. The derivative. But I've never differentiated, okay? This filters the signal and at the same time gives you a filtered way of the derivative. So this would be another way. But once again, it's based on frequency here. Okay, it's based on hypotheses, then not structural hypothesis, but a frequency hypothesis. But if you do something like this, you do not need to measure, but if you put something like this, you see, if I put a spring here, what I do here, I basically have only to measure this position because it's a spring. So how do you calculate the force you apply, which is the one you apply to the system? You measure this position, the one of the system. You have this position, a state of your controller, which you know. You take the difference, you multiply for the stiffness, you get the force, you apply the force. You see? You only need to measure the position, right? Okay, so that problem solves. I don't need to measure the velocity. If I do it with the sampling idea, I also have solve the problem, the interconnection between the digital realization and the continuous time realization. Okay, there was another problem, is that if the motor cannot give you more than a certain force, right? Well, that's not a problem because something like this, what is it? This position force, this is the motor, right? The saturation that you have in the motor. Well, it's not a big deal because if you take the square of this, what is this? This is a spring, which is a nonlinear spring, which is quadratic until that point and then goes straight. Okay, if you take then the gradient of that, you get flat, straight, flat. So you can actually, this spring is a nonlinear spring, which has a potential energy, which is basically quadratic, and then goes straight. So you see, I've solved this problem without any crazy things by a physical equivalent principle, and I solved two problems which are there, which are I can only measure position, and I have a nonlinearity. This is a nonlinear control design which works, and if you implement it, this is what you do if you do PD at 30 Hertz, and this is what happens if you do the same things with this. Okay, so it really is very robust, works all the time, and has no problem with with its passivity, okay? This is nonlinear design because, I mean, the thing is nonlinear, so it's a nonlinear controller, okay? But completely from a physical equivalent principle point of view. Until 5:30, yeah? So let me finish this part. Okay, so what you also can do is, of course, as I said, you to do more intelligent design, which is basically, you will work it here. So without doing the control, the first thing you can do, and this is really mechatronics. Mechatronics is sometimes used as buzzwords, but if you, real mechatronics is really looking at the change of the dynamics in a holistic way, okay? And for example, what we did in the lab in Twente is, suppose you want to build a 2D cheetah kind of thing, so motion. So what we built is basically, in something that I will show you how it works, first oscillations, 2 legs that oscillates. And basically the controller, which is physically based, I'll show you later, it basically injects energy and takes care that you have 2 things that oscillate at a certain height. That's it. And then you say, okay, I want these 2 things without any controller MIMOs that measure one or the other. We want to build a connection, a physical connection between the front and the back, such that if whatever phase it has, when I put it on the ground, it starts walking. It's like a cat which is, you know, there have been terrible experiments, cats which have been cut from the cortex, and due to the CPGs, they basically kept on walking. There have been terrible neurological experiments, but it is something that also physiologically is what happens due to CPGs. And this is exactly what we did, and this is the cheetah. So this thing is not controlled. Okay, you basically have these 2 oscillations of the front and the back, and due to the fact that the springs which you see here in the back is properly placed, this thing just walks forward. Okay? So it's really by intelligent design. And of course, this is what we want to do. This is here at ITMO. We actually want to go further with this and make it multidimensional. So you have the same kind of design concept, but then to have a multidimensional motion in all directions. Other things that, for example, you can do, this is a device I don't have the time to explain. If you're interested, I can show you. This is a patented variable compliance actuator. This is a device that by design can basically adapt the stiffness in a certain way, and you can build it in prosthetics and in other things, which really change the way the stiffness coupling between parts. Okay, this is also controlled. This is smart design, but you do it to do control on a physical system. Okay, so for me, I don't see it make a big difference between working with PDEs or building good stuff. I mean, the same thing. The goal is what counts, and the goal is to make stuff that works better, okay? Okay, this is another thing we're working on, in which you have to do with the rigid body, because this thing flies. This is basically a drone which pushes on a surface which is straight, and basically there is a mobile robot. Okay, but a mobile robot, to move, you need force to apply force with the wheels. But if you have gravity, that's fine, because gravity helps you. You have enough weight, you can move around. But if you are on a straight wall, you have to push it. So the drone basically just apply a force, and the robot moves. You see, what the heck do you use this for? Well, think about it. Whatever you want to inspect, which is very high, windmills and offshore applications, or a big building, you want to measure with NDT sensing or something, this is big business. This is something which you will see this stuff all over the place in a few years, okay? Because you don't need to scaffold anything. Nowadays, if you want to do something, you need to scaffold stuff and go there, or people need to go to rope and to take measurements. You just drive a drone and drink a cup of coffee, and that's it, okay? And this is something which also we won a Best Paper Award on a robotics and automation letter. Look at this drone. It just flies straight against the wall. It creates these systems like a damper, absorbs the energy, takes the measurement, flies away. Okay, and this was, we won the Best Paper Award of Erala 2 years ago. Okay, now, let's see, 41 is about halfway now, eh? No, but let's now stop 10 minutes, and now I will go more in detail. So now I have gave you a more broad view, and I will show you more how you actually implement some of these tricks in more details, okay? Good.